In this video, we begin our discussion of a second approach to multiple regression, stepwise multiple regression, or consistent with our the good, the bad, and the ugly theme, the bad. It's the Lee Van Cleef of multiple regression. Stepwise multiple regression is the answer to that inevitable question of why don't you just pick the best set of predictors for your regression model? Well, that's what stepwise multiple regression tries to do. So how does one pick the best set of predictors? You do it through an awful lot of fishing. In this case, fishing for effects. You start by doing two things. First, you need a list of possible variables that you may want to include in your final regression model. It may be a long list. Now, all of these, maybe most of these variables won't end up in your final model. It's just a list of variables that you think may have an effect and you want to consider for possible inclusion in your model. You then decide on specific criteria for determining what to add or drop from your model. We'll talk about the details for this criteria in a minute, but in essence it comes down to variables being statistically significant or close to significant, and which variables have the largest effects based on their t-score or f-score or unique variance, their squared semi-partial. Then, based on your list of possible variables and this criteria, you iteratively add or subtract variables to or from your model in a series of steps. Let's go through those steps conceptually first, before doing an analysis. Okay? To begin, we find the variable with the largest effect based on our criteria. Maybe the one with the largest absolute value for a t-score or the largest squared semi-partial. And we add that variable to our model in our first step. We then iteratively repeat steps where we add or subtract variables. First, we check all the variables already in our model to see if any of them no longer meet our criteria. Again, these variables are already in our model, and they must have met the criteria to get into the model. But maybe as we've added new variables, they no longer meet that criteria due to overlapping variance or shared effects with other variables that we later added. Now, if one or more of the variables in our stepwise model no longer meet our criteria, we drop the one that has the smallest effect. We drop it out of our model. And then we go back and reevaluate this updated model without that variable. On the other hand, if all the variables currently in our model still meet our criteria, we go on and evaluate all the variables not yet in our model from that original long big list of possible variables to see which ones, if any, meet our criteria. If any of them do meet the criteria, we see which has the largest effect and then enter that specific variable into our model and repeat the process all over again. On the other hand, if none of the variables not in our model, right, there aren't yet still in our model, if none of them meet the criteria, then we're at a point where we can stop the model building process. Notice that each iteration, each of these steps of the analysis results in a new model and a new set of analyses to compare those variables. In our output, we'll see that each of these iterative models are numbered, reflecting their order in the model building process, with each step reflecting the addition or removal of one variable to or from the regression model. So the first analysis with one variable in the model will be model 1. And the second analysis with 2 variables will be model 2, and so on and so on. In the end, every variable in our final model will meet our criteria, and none of the variables that are not in our final model will meet the criteria. So what are these criteria that I keep talking about? Well, as I said, there are different criteria or rules that people use. A common one is based on p-values, and it involves a pair of rules. What does it take for a variable to be added into our regression model? And what does it take to kick a variable out of the model? The p to enter or p in rule says that for a variable that's not already in the model to be added into the model, the p-value must be less than some value, typically 0.05. In other words, if it's not statistically significant at the 0.05 level, it won't be added. Think back to our basketball analogy. If it doesn't make a significant contribution, it ain't joining the team. The p to remove or p out rule says that for a variable that's already in the model to stay in the model, the p-value must be less than some value, typically 0.10. If the p-value is 0.10 or more, it can be kicked out of the model. Now, it may not be removed right away if other variables have even larger p-values, but sooner or later, if the p-value stays 0.10 or more, it will be removed. Notice that because p in is 0.05 and p out is 0.10, the variable only gets into the model if it's statistically significant. But they can stay in the model even if p later on is a little above that 0.05 level. So you may wonder, why not just set p out as 0.05 as well? In other words, once it's not significant, kick it out of the model. The problem is that you can end up looping around with a variable going in and out and in and out and in and out of the model if the p-value is close to 0.05. By building in a gap between p in and p out, it gives us a buffer against that happening. Once the variable is removed, it requires more than just a small change in order to get back into the model. Okay? So that gives us an overall understanding about how stepwise regression works. Why don't we end the video here, and in our next video, we'll reanalyze the data from the simultaneous multiple regression example, this time using stepwise regression. Okay? Bye for now.